What about refrigerators and heat pumps? How would we measure their thermal efficiency? Well, they don't have thermal efficiency. Okay. So what's the nature of a refrigerator and a heat pump, and then how would we measure its performance or its efficiency? Well, it won't be thermal efficiency, but let's think about this for a minute. Here's how a refrigeration or heat pump system typically works. This would be an example of your refrigerator in your kitchen. You've got a compressor on the right-hand side that takes in saturated vapor that's a refrigerant, compresses it so that it becomes a high temperature, high pressure superheated vapor, puts it into a condenser, and that condenser loses heat to the surrounding, say, kitchen air. Okay, usually that's where refrigerators are located. So then this super hot, well, not super hot, it's at 60 degrees Celsius, it's enough to be uncomfortable, but this hot refrigerant then cools down. As a matter of fact, the purpose of the condenser is to literally condense the refrigerant, and there's usually controls at the exit of the condenser that are fairly simple mechanical things that prevent anything but liquid from going on. And so the refrigerant is now at 800 kilopascals, maybe 30 degrees Celsius. It's still too hot, right? 30 degrees Celsius is a lot hotter than you want your meat for very long, because the meat's going to go bad for sure. But now we've got high temperature and high pressure, sort of mild temperature refrigerant, and if we allow it to expand across an expansion valve, it's a liquid. Some of it will boil off, and when it boils off, it'll cool down. So say it drops to 120 kilopascals, negative 25 degrees Celsius. Now we can do something with this, because the low temperature allows us to cool a refrigerated space that's already colder than the surrounding air temperature in the kitchen. So you then run the rest of that refrigerant through an evaporator, and what it does is the liquid boils off in the evaporator, absorbing heat in the process from the refrigerated space, keeping your leftovers from going bad and your milk and whatever you may have. And the evaporator, similar to the condenser, only allows out a particular thing. Whereas the condenser only allows saturated liquid out at high pressure, the evaporator only allows saturated vapor out at the lower pressure. So maybe the temperature's gone from negative 25 to negative 20 degrees Celsius. Ideally, if the evaporator were perfect, it wouldn't have changed at all, because we would just have a phase change. But in the real world, sometimes you might add a little bit more heat there at the end of the evaporator and change the temperature after it has already changed into a vapor. So in a nutshell, this is how refrigerators and heat pumps work. Now, if you think about the point of a refrigerator, what are you really doing? Well, you're doing something different than a heat pump, right? The purpose of a refrigerator is to cool food, right? The purpose of a heat pump is to warm a house. Now, in the refrigerator's job of cooling the food, it's going to heat the kitchen air. If you've ever stood around a refrigerator, especially if you have a tile floor and it's cold, you probably felt that the tile's a little bit warmer around the refrigerator. That's because the refrigerator is pumping out heat. Okay? But that wasn't the goal of the refrigerator. The goal of the refrigerator is not to push heat out and warm up the kitchen. Its goal is to cool down the food. Whereas a heat pump, its goal is to warm up your house. Now, in doing that, the heat pump is going to, well, it's laughable to say it, but it's going to cool the outdoors a little bit, okay? Not enough where you could even measure it. Not even enough so that your neighbor could measure it, okay? The atmosphere is a huge thermal energy reservoir, so it's pulling thermal energy from the thermal energy reservoir, but that's not why you buy the heat pump. You buy the heat pump to then take that thermal energy, raise it up to a higher quality or a higher temperature, and then put it into your home. Okay? So the goal of a refrigerator or air conditioner and the goal of a heat pump are very different things. The goal of a refrigerator or air conditioner is to cool a space, keep a refrigerated space cold, whereas the goal of a heat pump, the desired output, is QH, the heat that's transferred into the already warmed space. The required input for the two is essentially the same. It's the work you put into the compressor. You still have to pay your electric bill to make this happen. Okay, so that's the required input, but the desired output is different between the two. Now, common features of refrigerators and heat pumps, just like heat engines, they use a working fluid, although they use something different. Technically, the working fluid in your car's engine is air. The working fluid in a lot of refrigerators is R22. Sometimes it might be in your car R134A. My house, I went to 410A, I believe it is, for my heat pump. It's just different refrigerants. I don't use air for it. There are air conditioners that use air, and they are used typically on jet airliners where they have plenty of power available, but they can't really afford much more weight. And so they have fairly lightweight air conditioners that use air to cool air. And so it works out well, but we'll see that a little bit later. Typical features of refrigerators and heat pumps is that they receive heat from a low temperature source. They use work to increase the quality, in other words the temperature of the working fluid, and they reject that high quality or high temperature energy to a high temperature sink. They also operate on a cycle, and I didn't have there, but they use a working fluid. So if we look at refrigerators and heat pumps and we're interested in their performance or their efficiency, we have to consider what the desired output and required input is. So for example, the refrigerator on the left hand side, the goal of having it, the reason you buy it, is to extract energy that has leaked into the compartment, extract that energy and put it back out into the kitchen. So Q.L at 360 kilojoules per minute is the whole reason for buying the refrigerator. What you have to do though is supply 2 kilowatts of power that you'll ultimately have to pay for as you run that power over time. You'll have to pay for it to your electric utility. You're not really trying to warm the kitchen, but that is a byproduct. The house, on the other hand, you're not trying to cool the outdoor space. That is where you get 5 kilojoules worth of the energy from. You're using 2 kilojoules to move that energy into the home at a higher temperature. So you got to increase the temperature of it and then move it into the home. But your goal there is to warm the home with that 7 kilojoules of energy. Now in the real world, not all of the work that you pull in makes it into the house. Not all the heat that you pull in makes it into the house. But for the sake of what we're talking about here, this is fine. Notice that we could talk about the desired output over required input in either rate form, like we're doing with the refrigerator, or energy form, like we're doing with the heat pump. Either way would be okay, and we get the same result. So we can make these a little more abstract and just consider them as devices that are pumping thermal energy from a low temperature source to a high temperature sink. And of course the goal of the refrigerator is pumping from the low temperature source. The goal of the heat pump is pumping to the high temperature sink. And now we have our desired output over required input. Our desired output, and not really that it's an output of the system, but it's a desired result. It's the point of having the thing in the first place. The point of having the refrigerator is QL, right? And oh, by the way, you got to pay for the net work that it consumes. Okay, and you can write that, as I said, in power form as well, a power ratio. And this would be the coefficient of performance for the refrigerator. For a heat pump, it would be QH over the network, and the reason it's QH is because that's the point of having the heat pump. You wouldn't talk about the coefficient of performance of the heat pump in terms of QL over work in, because you don't care about the heat that it draws in from outside. You don't care that it cools down the outdoors just a little bit. That doesn't matter, and you're correct to say that. It is totally irrelevant. Your purpose is to keep the house warm. Now the network in, even in this case, will be the difference in the heat flows, because an energy balance around either one of these devices still yields this equation. And so we can make a substitution for the network in terms of the heat flows and rewrite our coefficients of performance for the refrigerator and for the heat pump, and you can see them there. It would be wise at this point to go to the back of the chapter in the summary, find these equations, and make a note of it. Don't try to use thermal efficiency for these two. Instead, use these coefficients of performance. And you might look at it and say, well, why did we rename it? Why don't we just always call it efficiency? Why call this a coefficient of performance? Well, if in thermal efficiency you get an over 100%, you get over unity, you know you've done something wrong, right? Because you're never going to get more energy out than you put in. So you've done something wrong. But here, since the goal is different, you can actually get performances greater than 100%, and the only reason for that is that work is actually a very valuable form of energy that can move thermal energy around. Basically, work can master the thermal energy. It can bend it to its will and make it do whatever it wishes. And the limitations on how much heat, if you will, that work can move is different than how much work you can get out of some heat. And so these coefficients coefficients of performance can easily go above 100%. It doesn't make sense to talk about an efficiency greater than 100%, so we call this performance instead. Mathematically, if you're curious, it turns out that the coefficient of performance of the heat pump equals the coefficient of performance of the refrigerator plus 1, but that's not really particularly relevant. Now, the Clausius statement of the second law is a little different than the Kelvin-Plank statement, and I've left it till now because it relates better to refrigerators and heat pumps. He said, it's impossible to make a device that operates on a cycle and produces no net effect other than the transfer of heat from a low temperature body to a high temperature body. Basically, he was saying that heat's going to flow from hot to cold. You can't make a device that takes in no energy and makes it go the other way. It's just not possible. Okay? So he said this is impossible. The Kelvin-Plank and the Clausius statement are actually the same thing, and it's interesting to consider this. Think with me for a minute. This will require a little bit of thought experiment. What if Kelvin and Planck were wrong? What if they said you can't take heat into an engine that operates on a cycle and convert it all to work and do this continuously, right? There's no way. What if they were wrong? What if we could? What if we had a heat engine where we pulled in a thermal energy amount QH and we converted it all into work? Well, then the amount of work would just be QH, wouldn't it? Because we're not going to assume that energy is created from nothing, right? We're not going to break the first law. But let's just say that Kelvin-Planck, they didn't know much. And so the heat engine converts all of the thermal energy into work. Well, we could then take that work and run it into a refrigerator to pump heat from a low temperature reservoir up to the high temperature reservoir, in fact the same one, that we extracted the energy from the heat engine. So if we did that, how much heat would flow? Well, I don't know, but we could call it QL, right? However much heat is pulled from the low temperature reservoir would just be QL. And now we've got the network coming in, which was QH, and QL coming in. Well, those two together, because of an energy balance around the refrigerator, would just be QL plus QH, and that's what has to flow up then to the high temperature reservoir. But if that's the case, you can kind of put your hand over the heat engine and the refrigerator. Basically, forget the details, that little workflow between the two, and what you notice is that we've got a combined system that has QH coming down, QL coming in, and then QH plus QL going up. Well, the QH down and QH up just cancel. They're the same amount. And so what we end up with is figure B, where we have a refrigerator that's effectively taking no work input and only moving thermal energy from the low to high temperature reservoir. And so we started off breaking the Kelvin-Planck statement to show that it is equivalent to breaking the Clausius statement. So let me put it to you this way. There's a couple of things you probably believe and one thing you might not. You probably were okay with the Clausius statement of the second law, that you can't make a device that moves heat from low temperature to high temperature on its own without any work. You're probably okay with that, and the reason you're probably okay with that is because you know heat doesn't flow from cold to hot, it flows from hot to cold, right? So that probably was not too big a pill to swallow. But the heat engine, the Kelvin-Planck statement that you can't just take in heat and convert it all to work, you probably in the back of your mind thought, I wonder, is there a way to do it? Well, if you believe the Clausius statement, you have to believe the Kelvin-Planck statement. They are the same thing. There is no difference between the two. The logic leads you to the idea that they are equivalent statements of the second law. So if you believe heat won't flow from cold to hot with any device you were to build, and a lot of people have tried, then you also believe that you can't take heat and convert it all to work. Some of it has to be thrown away, and that's a very important result to obtain. There are many different kinds of perpetual motion machines, and they're categorized by kind. There's perpetual motion machines of the first kind, and the idea here is that these are perpetual motion machines that generate energy from nothing. They break the first law of thermodynamics. They say, energy conservation, no, that's wrong. We can just make it from nothing, from the ether, okay? And so a statement like that would be something like, well, you know, we're firing this boiler down at the power plant, and boy, the coal sure does cost a lot. And we know that the generator generates a whole lot of electricity, and why don't we just put a resistance heater in the boiler, take some of the electricity that the generator is generating, and fire the boiler?
And then we'll still have some network out. We can sell our customers. We'll fire the boiler. We won't have to pay for coal anymore, and everything will be good. We're not going to try to break the second law. We'll throw away the waste energy out of the condenser. But if you think about this with a system boundary around the whole thing, what are you doing? Well, notice we got Q out and we got network out. There's no energy coming into this system. And so if this is something that is supposed to operate on a cycle and operate continuously, this won't work because it's generating energy from nothing. So this breaks the first law of thermodynamics. It says that energy is not conserved. If you ever make this type of system, you will shake the foundations of everything we think we know. Okay, because it's believed that energy is conserved. We've never seen a machine that could break that law. And the law actually predicts, it has extremely good predictive power in many different branches of science. And so I really don't think that one's going to be broken. But this is a perpetual motion machine of the first kind because it breaks the first law. Perpetual motion machines of the second kind are the kind that break either the Kelvin-Plank or the Clausius Statement of the second law. And so you see here what's being broken is the Kelvin-Plank statement because heat's coming in and work's going out, but there's no waste heat being thrown away. And so this system is the one where we've removed the condenser. We said, it's foolish to boil off the water and just to recondense it after the turbine. We're going to just let it go through the pump instead. Well, this won't work. You won't have a machine for very long, and of course you can't just convert all the heat that comes in into work, mainly because heat doesn't flow from cold to hot on its own or with any machine to help it along. So this is a perpetual motion machine of the second kind because it breaks the Kelvin-Plank statement of the second law. If it broke the Clausius statement, then it would also still be. Of course, it is because they are the same statement, or at least they are equivalent statements. They aren't the same statement, but they are equivalent to one another. There are a lot of so-called free energy devices out there. Some of them break the first law, some break the second, some break both. Why not? Go for broke, right? A lot of times you'll notice that they're associated with conspiracy theories. Oh, big oil doesn't want this device to work. Watch this video before it's taken down from YouTube, things like that. These devices are often well-intentioned endeavors or they're money scams. I mean, they can be either. A lot of people don't understand thermodynamics well enough and haven't thought it through well enough to realize that free energy devices won't work. They're just not going to happen. You can do a YouTube search for free energy and find all kinds of interesting things, and I would not dissuade you from looking it up. I would encourage you to, in fact. Sometimes some of these devices are very clever, and you might be challenged to look at it and figure out why it won't work. But often there's a mechanical reason that goes back to breaking the first or second law that shows why it will not work. The overbalanced wheel, for example, is one of the easier ones to figure out why it won't work. But the whole idea there is that you allow a weight to go out as it's falling and it comes in as it's rising. And so the idea is that the torque that it provides, the moment on the rotating wheel, will be more in one case and less on the other. Of course, the solution to that is that when these weights are out far from the center of the wheel, they're also spread out. They're not as concentrated. So on the other side where they are closer to the center of rotation, they're very concentrated and, they cause as much of a moment as the moment on the other side. So I found a book once in the library back when I was studying. I wish I'd written down the name of it. It was really interesting because it was a whole book of free energy devices, basically just perpetual motion machines from back to front. Some of them were extremely clever, and I really struggled to figure out why they would not work because everything looked like it should work. It was just purely a mechanical system, and it looked like it should work, and yet they don't. And so it was good study for a while to look at that and figure out why this next machine could not possibly work.